Great, thank you very much. So given that we're 5 minutes behind the schedule, you will also get these 5 minutes, of course, at the end of your talk. So we will start the coffee break slightly later. I hope that's fine with everybody. Yeah, we can get started. So it's a great pleasure as a third speaker of this online day of continuous optimization to have here Professor Coralia Cartis, as I said already, from Oxford University. Coralia is a well-known expert on numerical algorithms and continuous optimization, particularly in connection with the regularization methods, trust region methods, and in general complexity analysis for non-convex optimization, a very challenging and very important topic, and one of my favorite topics also in the last years. So I'm very happy that she's here and giving a talk for us. So Coralia, the floor is all yours. Please go ahead.
Thank you very much. Thank you very much, Matthias, and the rest of the organizers for this very nice invitation. I hope the days are coming when we can see each other face to face, but I'm happy for technology so that at least we can see each other this way. So indeed, I very much was thinking whether I should talk about deterministic or stochastic things. So I've decided to go for this one, and I have a little surprise at the very end. So this is, I thought also the topic was kind of to give some kind of survey a little bit. So I've tried to do that. So this work indeed is about my long-term collaboration with Nick Wood and Philippe Toin on complexity of non-convex optimization. So I want you now to think that I just have a general function f that's smooth, and I'm going to try to find a local solution, and I'm going to do that. So a small gradient and a local, approximate local convexity. And how I'm going to do that, I want to start from any initial guess of the solution in this method. So I want to start from any x0, and then I want to approximate at every iterate my complicated, potentially non-convex function f by some simple local model, like a linear or a Taylor or a linear or a quadratic Taylor model. And then I want to minimize that local model instead of my function locally and advance in this way, then construct another model and so on until I generated a small value of the gradient. So I have here, if I have a linear model, I would have a steepest descent or gradient descent like direction. If I have a quadratic, I have the typical Newton direction. If I just keep taking these directions and do nothing else, I will not get a convergence method from any starting point. So what we need to do is to safeguard these methods with some standard techniques that you are all familiar with: line search, trust region, or regularization techniques. So we have to control the length of the step to ensure convergence from an arbitrary starting point. And what we notice, though, is that from a complexity point of view, which I very much want to focus in this talk on, first order and second order methods for non-convex optimization can be very similar. Locally, Newton, so second order, is much faster than first order. Second order less affected by conditioning of the problem than first order. However, globally, from an arbitrary starting point, they can take a similar number of steps. And this is an example that shows, a constructed example that shows in 2 dimensions that Newton can be as slow as steepest descent and require epsilon to -2, essentially epsilon to -2 evaluations, same as steepest descent, to drive the gradient below epsilon. This is on a function here that is that has Lipschitz continuous gradient, Lipschitz continuous Hessian. It can have we have various examples. It can have well-defined minimizer or just an infimum. Various examples are possible. And so what we have found was that classical methods, line search, trust region, so first order, second order, from a starting point, arbitrary starting point, for non-convex problems, they look about the same. So here's a table of complexity bounds. Epsilon, steepest descent, epsilon 1 for the tolerance on the gradient to -2, Newton globalized with trust region or line search or anything you want like that, classical technique, same to drive the gradient below epsilon. We can also estimate the second order complexity here. So to make the Hessian sufficiently close to being positive definite, so the smallest scientific value larger than -epsilon2, we get this complexity. So is there something better? If you globalize Newton-like directions with regularization, so you safeguard the step with the regularization technique that I'll describe in a moment, you get better complexity. For first order, for the second order, it's the same as for trust region. Indeed, in fact, these bounds here are optimal. This first order bound is optimal for second order methods. And then trust region variance and line search variance were devised that match the same complexity of epsilon to -3/2. So it's possible with classical methods to improve on the complexity, on the standard complexity of Newton and steeper descent by some more sophisticated techniques. So sharp, these bounds are sharp and they are optimal. So what is this ARC approach or cubic regularization? You may be familiar with it, but after I tell you this, I'm going to start talking more about tensor methods. So the framework here is important for what follows. So I told at the start that we are going to approximate our complicated function by a local model. So in regularization methods, in cubic regularization methods, this local model is the second order Taylor T2 expansion, right? So a quadratic model plus a regularization weight, sigma k, and then the 2 norm of the step to power 3. So the power here is 1 more than the order of the Taylor expansion here, or the degree of the polynomial. Then what we need to do is to minimize this model. This model is always bounded below. It's suitable for minimization. What we need to do to calculate the step is to just do some approximate local minimization. So we don't need to do anything global. The global minimum exists and it's well defined, but we don't need to calculate it. It's enough to just get strict decrease from the current value at s equals 0, so the base point, and an approximately small gradient of the model. And if you are calculating second order critical points, then also a non-negative, sufficiently non-negative local point for the second derivative. Then we measure progress. So we want to see when the function has, when we have decreased this model by calculating the step, and then also the gap between f and the Taylor expansion has decreased. So this is always positive here, unless we terminate. Does the function decrease as well or not? If the function decreases about the same amount as the model or more, then we take the step. Otherwise, in particular, if the function goes up at the trial point xk plus sk, though the model has decreased, then we stay at the same point, and the only recourse we have is to increase the regularization weight. Increasing this sigma k is like a penalty on shrinking it reduces the length of the step. We also allow the regularization weight to decrease from time to time to prevent steps from becoming unnecessarily small. So this framework was discovered independently by a few people, Grivenk, Nesterov and Poyak, Weiser and others. In particular, Yuri and Poyak, they showed the good complexity bound of epsilon to -3/2 for the first time. Now, what I want to talk about next is, what if we have more derivatives? So I know we live in a world where we try to go the other way, but there are many problems, and the days are coming when maybe we can use this higher order information. So what if we have third order information? Can we make use of it in the algorithm? So I'm going to build on the regularization framework exactly as it was in the previous slide. So let's try a very simple generalization. The second order Taylor, I'm going to replace it with fifth order Taylor. So assume that I have derivatives all the way to pth order. And then I'm going to regularize my model with my weight here and the p+1 power of the step. So one more order than the Taylor series. And then the conditions for model minimization are the same. So still the model is bounded below. The minimization here are changed appropriately, let's say, not identically the same, but changed appropriately. So I have to minimize here to order P and here to p+1 in terms of the power of the step. This condition stays the same. So still approximate here first and second order local solution of the model. This is what I'm doing in the model minimization. The rest of the steps are the same, except I replace T2 with TP. If I manage to, so when I decrease my model, have I decreased my function? If so, I take the step, otherwise I stay at the same point and increase the regularization. This simple change allows me to get a better complexity bound because I expect it to be better because I have more problem information. So under what assumption? So assuming that the pth order derivative of f is Lipschitz continuous, okay? For the cubic regularization result, the condition is that the Hessian is Lipschitz continuous for cubic regularization. So here we just say, so the second order derivative Lipschitz, here we say the pth order Lipschitz. And then we get this bound here for epsilon1 to minus p+1 over p for getting the gradient below epsilon, and here for ensuring positive semi-definiteness approximately of the second derivative of f. Of course, if you don't want care about the second condition, then you just have the first bound. And here in this table, I plotted what these values p+1 over p become. So for cubic regularization, it's here, epsilon to minus 3/2. For p equals 3, you get epsilon to minus 4/3, and so on. So this improves as p grows, as expected. Before, we only knew methods for ensuring second order criticality, we only knew methods that have this complexity of epsilon to minus 3. But with this bound, with these methods, these pth order methods, this bound also improves. Furthermore, this bound for first order is optimal. This was shown in the Carmon paper. And we have sharpness examples as well, and another kind of constructing lower bounds as well. Okay, and we've also shown sharpness for second order as well. All right, so we can improve now. So we are able we have pth order derivatives, and we can certify first order criticality for f and second order criticality for f. So we started to wonder, but if I have such higher order information about the derivatives, what about certifying higher order criticality? So at the moment, I can just say this is an approximate second order critical point. But what if I have 0 eigenvalues of the Hessian? There I cannot certify if I have a minimizer or not. So I need to go to higher order criticality. What is even higher order criticality? For third order, we know. Oh, sorry, I'm jumping ahead here. Sorry. Okay, so forget about third order. Hold that thought for a moment. I want to give you some ingredients of the proof because it's very simple. So still first and second order, I want to prove those better bounds to you. So on every successful step, we know that the function will decrease by some amount. So it will decrease by a multiple of the Taylor decrease. But this I can write then in terms of the model. So the Taylor is the model minus the regularization. So I plug this in here. I've required that my step gives strict decrease from f. And so this term here is positive. This term is, of course, non-negative. So I immediately get this. This lower bound on sigma is just something that the user says that, look, I'm not going to allow very small regularization. It's user chosen, can be anything. So I can bound the function decrease as a multiple of the step. And then what I need to do is to relate the length of the step to my optimality measures. For first order, I can relate it to the length of the step. And this is where the Lipschitz constants come in. So in this relation between connecting step to optimality measures is where the Lipschitz comes in. And so the step can be lower bounded by the gradient to 1 over p. And for second order by the smallest eigenvalue of the Hessian to 1 over p minus 1. So this is where the Lipschitz properties are crucial. So until I terminate, I know that this is above epsilon 1 or the Hessian is greater than minus epsilon 2. Also, the regularization stays bounded, so I cannot forever decrease the step. That's also based on Lipschitz properties. Right, so now if I can bound the length of the step as a multiple of epsilon 1 and epsilon 2, I can plug it back in there. At all the steps where I don't make progress, there is nothing happening. And then on the successful steps, I get the some quantifiable decrease. And so my complexity, since the gap between fx0 and f star, the function decrease cannot go below that, then I can bound this. I immediately get the complexity to be, when I sum up the decrease, a multiple of the inverse of the term here, the reciprocal. So that's it, basically. Right, so third order. So for third order, we know that the third order derivative at criticality, at a local minimizer, the third order derivative is 0 on eigenvectors, along eigenvectors corresponding to 0 eigenvalues of the Hessian. That's the second order, that's the third order criticality measure. So what we were able to do, we were able to quantify this algorithmically, so we can have a model condition that's similar. So we minimize the model to an approximate third order criticality condition. Under the same condition that the pth order derivative is Lipschitz continuous, we can also quantify how long it would take to ensure a third order criticality condition. And here's the bound, and it changes predictably. Okay, so, right, but I have pth order derivatives. So why can't I certify pth order criticality? So higher than third order. Well, what is higher than third order criticality, right? So this needs some thinking. So let me see how much time I have. I think I have a bit more time. So I don't want to bore you with all these details.
10 minutes more, I would say, and then we can have discussions for sure.
Okay. So what happens along beyond third order criticality? How could you characterize such things? Well, we think about criticality as, to get first order criticality, you think about how at a minima, you don't want to have descent lines. For second order, you can get second order criticality conditions by thinking that you don't want to get, you're not going to get descent along quadratics. Whenever you have, 0 eigenvalues, you don't want to get further descent along quadratics. Similarly, for third order, you don't want to have descent third order arcs, essentially. So by the same kind of methodology, you can start looking at what are necessary conditions and sometimes even sufficient for higher order criticality. And what you can do is simply by saying, I don't want arcs, algebraic arcs, I don't want descent, then you, so I want for alpha sufficiently small here, I want that f along these arcs does not go down. So by collecting terms and saying, okay, if the first term, if the gradient is not 0, fine. If the gradient is 0, then what has to happen to second order? Well, we know the usual conditions. If you have first term 0, second term 0, so this is what this condition is saying, that I'm in the kernel of these intersections of polynomial forms, and so when then I have to go to the next order and so on. So whenever I have a 0 term in the expansion, I have to have no negativity for the remaining terms. Okay, so but what this is telling me is that these forms are very complicated. These conditions are very complicated. Okay. Furthermore, just a clarification here. At a local minima, you don't necessarily, you cannot fully characterize it in terms of descent along algebraic arcs, because you can have that the function, a non-convex function, can still decrease along non-polynomial arcs. Okay, so that is possible, and this is the famous piano example. And so even these conditions with algebraic arcs, even though they are complicated and they try to capture more beyond, than first and second order, they will still have their limitations. But still, they extend everything we know much further than usual, I would say. The other thing to notice is that you can say, okay, so let's assume that so first order can be the first order condition just involves the gradient. The second order condition, you can separate it to just be something on the hash, and same for third order. Pretty much, like you can decouple them. This is what I mean. You can decouple them in a nice way. However, once you get to fourth order, there are simple examples that show that if you decouple them and you just say, I just want a condition on my fourth order term, that fourth order term is non-negative on the intersection of all the other kernels of the derivatives, what happens then is that the condition is so weak, it's practically meaningless. So to get anything meaningful, you cannot decouple anymore beyond third order. This is one thing that we realized, okay? So you have to find new optimality measures to characterize higher order criticality. And this is what we did, and what we proposed is a nice measure, an easy measure that doesn't have all those complicated terms I just told you, and just looks at the maximal change in the Taylor expansion of the function around the current point in a ball of a certain size delta. So I take around x, or my candidate point x star or xk, I take a ball of size delta and I look at, does the Taylor expansion change from my base point there? And this value of delta also can change, the size of the ball. And what you can show is that a suitable measure here is that this maximal change in the Taylor model, where now I have definitely global minimization for it, goes to 0 as delta j. So this at a minimizer. So this phi j itself goes to 0, but that's also too weak. So it goes to 0 as delta to j. Right, so this is our measure. And it involves global minimization. And what you can say is that so you can have Q's order criticality, and you have all these measures up to order Q to certify a Q's order critical point. What is a suitable regularization method here? Very similar to before. I'm going to have the same model, and I'm going to change my condition on the step minimization to involve my new measure phi, this maximal change in the Taylor for the model. But now I also have to calculate the size of the ball on which properties hold. So I need this kind of transregion-like ball on this regularized model. The rest stays the same, but I have to think what to do with this transregion size as well. And what do we get for complexity? For first and second order, we get the same as before. But once we have higher than second order criticality that we are looking for a fifth order regularization model, then we get this bound here, which is slightly worse, but it's also certifying this very strong condition of order delta j. And these are kind of the first kind of results that we know for regularization methods that can do this. So we can quantify Qth order, where Q is less than P, can be equal to P. So if you have these derivatives, you can certify higher order conditions. You could say, why is there a gap here? Why does the bound not change continuously? It's to do with the strength of the optimality measure. If I let this delta j here be just delta, so I go for a weaker optimality measure, then this bound here just would remain the same all the way to Qth order, and the J would change to Q. Okay, or you know, it stays. You can generalize this to higher than to second order criticality. Okay, the proof is very similar to before. You have this a multiple of the step, and then you bound the length of the step using the new optimality measure. Okay, we can do truss region, we can do inexact derivatives, convex constraints, composite case. So we have all these extensions. Okay, I need to finish in another 4 minutes, I think, right? I started at 9:35.
Yeah, well, we said we give you 5 minutes more, so it's 1:15 we should finish for the break, so 5 more minutes should be fine to have enough discussion time.
Okay, thank you. So we can also do universal regularization methods. So here, another variant, I have pth order Taylor in my model. And now I wonder what happens if I regularize by something else than p+1. I can change the algorithm easily, okay? But to get something better and more meaningful in the complexity, as I will describe in a moment, I'm going to constrain the step a bit more. So I'm going to only allow steps that have the right length, okay? And what that means is that these conditions here are satisfied. This condition for first order and this condition for second order. And so I'm very careful with what steps I take. And if these conditions are not satisfied, even though I have a progress in my function, I decrease my function, I recalculate the step until I can ensure them. But one can show that if the regularization is large enough, this will hold. So what does this extra condition gives me? So now I'm doing just first and second order again. You know, I kind of just stopped with Qth order criticality. So I'm just doing first and second order. I want to look at the different question of what do I do if I have a different regularization power here. I require these extra conditions because I also want to do something else. I want to loosen the smoothness assumption. So before I had that the Hessian was Lipschitz continuous. Now I want to loosen it to Holder continuity. Assuming that, you know, there is some smoothness there, but I don't know the parameter. So I don't know the Holder exponent. I know it exists, but I don't know it. So as you know, this is a weakening of the smoothness assumption, and it's often like a bridging case between smooth and non-smooth problems. So this beta p is meaningful between 0 and 1, including 0, and at 1 we get the usual Lipschitz continuity. So coupling this Holder with these additional conditions on the step allow me to show for regularization methods this universal-like property that for first and second order criticality, we can extend the bounds continuously. So if beta p is 1, I get the bound from before here. But now I allow beta p to be between 0 and 1. Okay, so, and I don't assume to know it in the algorithm. Beta p, the exponent in the Holder, does not appear in the algorithm. So the algorithm's complexity adapts to the smoothness of the landscape. And we were able to also do second order criticality, which to the best of my knowledge has not been done for this kind of universal approaches. Right, so various extensions to regularization methods that we've considered and we've analyzed them from a complexity point of view. And all of this is going to hopefully come up in the summer, in early summer. Is now with Mosayem Publishing. We are going to get the proofs very soon. So it's in process and it will finally come out. It's been a lot of work for over quite a few years. Most of the things I said here are in our papers and in the forthcoming book where we try to cover these aspects and others. So thank you very much for your attention.
Oh, thank you very much for this wonderful talk and this nice overview. And I'm just wondering now, so what is exactly on the cover here of the book? I can't really read that.
So this is it's like the plaque from printing. So when you make like etchings, but it's actually the actual plaque on which you make the etchings.
I see.
Yeah, so we all had a go at trying to include some art of ourselves or our family members. So this is from Philippe Toin, and we have others in the book as well. But we hope this will not increase cost or something. So
we will see. Okay, so this is the command for everybody who's in the room now to buy this book as soon as it's out. Great. Thanks. We have now time for some questions.
Yes.
Yeah, Heidi, you please go ahead.
Okay. Thank you for this very interesting lecture. I'm impressed. Just, it's not a technical question, just a comment or some intuition. You see, your talk concerned non-convex smooth optimization. Okay, and in non-convex non-smooth optimization, there is an important ingredient which captures the geometry of a function is the so-called Criticality property. So I'm wondering whether this notion could be used in the case of non-convex smooth optimization.
So what we have done in terms of complexity, we have looked at more like the Poyak-Loyasevich. So where the gradient domination.
It's related.
Yeah. So we have also in the book, and you can also find it in other papers, not just ours. This idea of the gradient domination, as you know, and so from that point of view, you can analyze the complexity of these methods, and one of the sections in the book is on this. And what you can see, so what we assumed was that you have a domination with some power of the gradient, some exponent tau, let's say, and then you can see how your complexity is going to depend on this tau. And indeed, the complexity improves.
Okay, for sure.
Yeah.
You have more in geometric information of the function.
Yes, that's right. So the complexity improves, and then you start to see these phases. You know, you can start capturing the maybe some superlinear phase at the end, and a better bound in the beginning. You can also start capturing what happens to the function itself, not just the gradient. Sometimes. So yeah, we've tried to do this in a general way, where you just have some tau, and then you have, because the crucial ingredient here is you have the step that then is connected to the gradient, and then if you then from there you can connect the gradient again to the function decrease, and then you have those complicated recurrences that you have to figure out what rate they actually give you, and so we were able to do that in a very general way.
That's nice.
Chapter 5, yeah. But the non-smooth case, the only true non-smooth case we looked at was in the context of composite optimization.
Yeah, composite. Clear.
And there we didn't necessarily did this rates, but the way we set up the framework, it can be extended to that.
Okay.
Thank you.
Okay, we have a question by James Cock. I'm not sure if I pronounced this correctly.
Yeah, that was correct. Yeah.
Okay.
Sorry,
thank you.
I'm very new to optimization, and this entire event was very interesting to me. I just had one question, but it might be really basic. But why might someone be interested in like regularized local methods higher than order 2? Because I'm very used to like L1 and L2, but why might someone be interested in like a p-order regularization method?
So that's a very good question. So I would say there are two ways to answer this. So one is you want to ask yourself, how, from a theoretical point of view, we wanted to know, can I get better complexity if I have higher order information, and can I actually have an algorithm that takes account of that? Okay, so you can say that this, with mathematics, we are trying to stay ahead of the practice. Secondly, though, in many applications, you will have at least maybe partial higher order information. Maybe you can afford to take difference in Hessians, for example, or you can do difference in gradients, but you can approximate higher order derivatives with difference in gradients, right? So you can say, all right, so maybe I don't have that derivative, but what if I approximate those higher derivatives in my method? Will I get better complexity? And the answer is yes. Yes, you will. So these algorithms, I presented the fixed derivatives variant, but you can allow approximations, definitely finite differencing. We already have framework. There are other kinds of approximation that give you enough accuracy, but this is approximate accuracy. You can get similarly improved complexity. Now, I think that very often now, because we have a lot of challenges in optimization coming from machine learning, it's easy to forget that there are many other applications. And for example, I have colleagues at the national lab close to me that have derivatives galore, but they just want really fast methods. So for them, giving me more Hessians is not a problem. Even giving me partial third order is not a problem. So there are different applications that bring us different challenges.
Thank you. Makes sense.
Thanks for your question.
Okay. Yeah, great. I would have a last question, if you allow me. So sure. You said you're able to capture also convex constraints with your approach. So how exactly? So you would incorporate the convex constraints in the computation of the search direction, or later when you compute your feasible arc, so you choose the alphas appropriately to make the short step. How would you incorporate that exactly?
Right. So this is a very good question, and we kind of have two ways. So the simplest way to say is that you can say that you can just make the model minimization be over those convex constraints. So provided, this is all evaluation complexity bounds, and the cost of the subproblem that does not require additional evaluation complexity bounds is not taken into account of the final bound. And so if your convex constraints, if you can solve your models over convex constraints, this is true both for first and second order and for the higher order, but let's just say first and second. If you can solve your model over convex constraints, so if you can solve this cubic over convex constraints or piece order over convex constraints, then what we are able to give is a framework where the constraints naturally come in and they don't ruin your complexity. But it's at the cost of being able to do this subproblem over convex constraints.
I see. We
also try to be more precise about it and more and quantifying the complexity in a more appropriate way. Like, so we can do it very thoroughly with proper optimality conditions for convex constraints and so on.
I see.
Yeah, and we can do that all the way to third order as well. So we can fully do proper optimality conditions from first to third order. I mean, this higher order is possible, but it gets even more, theoretical in some sense that you have to be able to solve globally over constraints. But we can do it locally over convex constraints and certify proper constraint third order criticality. But how do you solve, how do you quantify the subproblem solve? Not in the evaluation, it's not going to matter, but computational complexity, that's kind of was a little bit beyond the scope in what we did. But practically, we do look at how to solve the subproblems up to third order, up to, well, the cubic model. We have quite a bit of work on that. But I think that what is outstanding questions here are how do you minimize these fifth order models efficiently, even locally? What are good models? What is their complexity? I think this is ongoing work. For example, how can you efficiently, what do you prefer to do with the constraints? We can say that if you can solve your problem to approximate accuracy, approximate local accuracy, not globally in the constraints, then your evaluation complexity remains unchanged.
Interesting. Okay. Well, for the sake of time, unfortunately, I think we should now have a short break, also to give us some time to refresh, grab a coffee, or do whatever we need to do. So let me thank you again all for being here, and in particular, let me thank all the three speakers of this first session of the Online Day of Continuous Optimization for these wonderful, very insightful talks. So thanks, Hedi, thanks, Mark, thanks, Coralia, for being willing to share your insights with us and giving us such a nice overview. I guess the community very much appreciates that.